Hello. Good morning, Devox. Welcome to the last day, Friday. So this is me, I'm Simon, and this talk is going to explore the intersection between software architecture and code. And really there are two things that inspired me to
I don't know what is going on, but no worries, we just will talk about trains, no difficult stuff about architecture or anything else. So if you're here for trains, you're in the right room. If you're here for a movie like Spectre, you're probably in the wrong room. We're going to talk a bit about trains. Together with my colleague Willem and myself, we will talk for the next hour about what we did with Lego trains. We don't work for Lego or another company that's producing toys. Normally we just build enterprise software for large organizations. But we thought this would be fun, and well, we can give probably a quite cool demo. And I mean, demos, they always go okay. You never have any issues with live demos. So we thought, it's Friday the 13th. What could go wrong if you have like 4 Raspberry Pis, a bit of Wi-Fi, and a couple of applications? So we will probably be all right. So we will show you later how it's working. First, of course, the disclaimer. You always need a disclaimer. I have to admit, although the Lego wasn't harmed, I harmed like 3 Raspberry Pis beyond repair, but I mean, that's cheap. The content for today is this. If you have any questions, you can also ask them in between. Just shout real loud and we'll try and answer them. But first, a bit of, why did we do this? I mean, it didn't just pop up like, oh, okay, we do Lego trains and the Ferris wheel, add some Raspberry Pis. No, we had a couple of reasons to do this. First of all, like I said, we mainly build large systems for large organizations on big servers, using Java or Scala and all the frameworks that you probably already know. And we were thinking like, okay, can we use those frameworks on IoT hardware, like the Raspberry Pi? Because if that's the case, then our developers could quite easily develop IoT software because they're already familiar with those languages and they don't need to learn some version of C or some other low-level language. They could start immediately. So that was one of the reasons we started with it. And one of the other reasons was it's a lot easier to use Lego and stuff like this to explain some concepts. For instance, if I try to explain to my wife what an event-driven architecture is, and I say it's sending a message X from position A to position B or something like that, then probably she stopped listening after event-driven. That's not her fault, but it's, I think, our fault because we have some strange dialect as developers, and it's hard to understand. But if we use Lego and I say to my wife, like, we send a message to the train that it has to play a song, then she can easily understand it. And I'm almost telling the same thing as I did before in some dialect language, so that makes it easier. And we can maybe also use it to educate kids with it. But as you can see at the top, it's also a nice project to just have some fun. Ingredients, so often I see like cool stuff and presentations, but it's hard to figure out what they actually use for it. So I thought like, okay, I just mentioned the different hardware that I bought to motorize these trains and to make them connected, because it's quite cheap. If you don't have a Raspberry Pi, it's about 50 euros. If you already have a Raspberry Pi, it's like 25 euros. So that's really cheap and you can already control the train speed. But if you want to go one step further, like this, here we already have like a camera on the left. We have a RFID reader at the bottom and a speaker at the back. Of course, you can keep adding, but then, of course, it gets a bit more expensive. But you can have more or less endless fun with it. So now my colleague will take over for a moment.
So if you have bought those trains, the rest is just adding more software to it. And my colleague is a very fan of buying Lego, but he buys a bit of bucket full. And there's also some architecture in there. So we started out with building an Angular application, a front end to control everything. I will show it later what it is. And we used REST services, Jersey and Java to start out and start building this whole project. And we use JSON to transport messages from the train control to the train and to the switches. But when we started working with Akka and Scala, we discovered that it's way easier to do the same thing with Akka. Akka has this messaging pattern. It allows you to send messages between actors, and you can easily convert a train into an actor. It's basically the same thing. There are a few tricks involved, which we'll show you later, but that's about it. So we replaced everything with Akka, except for the bit where we talk from Angular to Akka, because yeah, you can't just send messages to Akka from Angular. Maybe in the future. So how does it work on a hardware level? Well, we connected a few trains to Raspberry Pi using infrared transmitters. We reverse engineered the remote control that LEGO uses normally. And the rest goes over Wi-Fi. We bought a couple of cheap Wi-Fi dongles and inserted those. And the switches we normally use through Wi-Fi, but we switched to a cable because Wi-Fi has this very annoying property that it disconnects if there's a lot of people in the room. So it could disconnect over here too. Friday the 13th. I hope Murphy is out of the building right now. But that's about it. And we have an overview camera, which is in the corner over there, also connected to a cable. And we added, just for fun, we added a couple of Particle Photon computers, which are even smaller, about this big. You probably can't see it in the back, but it's a few centimeters, 2 or 3. That has a Wi-Fi chip and very small computer that you can use also to control things like LEDs. So how does this work? Akka has this principle of building actors that you can send messages. At the top you can see a class coordinator, and extends from an actor, and it has a receive method. You can't talk to actor directly. You have to send it messages because it's highly concurrent. And once you send it a message, you can do things like print a line, or in our case, you can control the RFID or the infrared controller. And finally, if you have an actor, you can make an actor system in which the actor is hosted. And you can ask the actor system to create a new actor of your choice and send it a message using the exclamation operator or the tell operation on the actor. So, okay, that works on a single computer, but we have this thing where the Raspberry Pi is in the train, and we have a computer controlling it. Akka has a very cool feature called Akka Remote Actors to do that. And what they do is basically, if you have an actor on the train, that's on the top, the code, it has a simple actor that's local. It's running and it accepts messages. You can even send a message to it locally and it will go at a certain speed. At the bottom we have the same thing basically, but remote. And the idea is you create a remote actor ref, but instead of creating the actor, now I'm going to ask for an actor on a different system. And you can see that by the string, Akka TCP, it goes to my example actor system at a certain IP address and a port, and it will ask for the /user/coordinator actor. And basically what this does, it tries to connect to the remote computer, find that actor in your actor system, and talk to it. And after that, it's just a normal actor reference, and you can send messages to it. So it's just like programming locally, but now it's all over the network. Apart from a little bit of code you need to change, there's also a little bit of configuration you need to do. There's an actor provider you need to configure, and it needs to be a remote actor ref provider, which basically tells Akka, okay, I support remote actors and I want to talk to them. And the other thing you need to do is to set up a remote connection, which enables Akka on one system to talk to Akka system on another computer. That's all cool, but we have a slight problem. Since we have now 2 applications, one on the train and one on my computer, I need to have a way to share a protocol between them, namely the messages we're going to send. So for example, I have an actor on my laptop, my train control actor in this case, and it's going to send a play message for a song on the train that's going to play across the speaker. But yeah, that message has to exist in both ends, because Akka doesn't use JSON or XML or SOAP or anything. It uses a binary serialization, so it means that you have to share the messages between one system and the other. And this is how we do that. We basically introduced a third library that contains only the messages we're going to use, and we set it as a dependency of both our server product and the train. So what does a message look like? It looks like this. We have a basic pattern in Akka where you say we have an actor class and we have a companion object with that actor class, and that companion object will basically define the messages that the actor can receive. So what you see here is an object music service message, and it has a play and a music list. And play accepts a file name that must exist on the train, obviously. I can't send whole files over the network right now, and it will play. And this is how it works in practice. So you ask for the music service on the train, and you send it a message that's coming from our message package to play your song. So I told you earlier that we did something with REST services in the beginning, and we moved from REST services onto remote actors. And there are a couple of differences between that. In HTTP, you have to send JSON messages. You have to serialize your data into JSON, and at the other end, you have to deserialize it. You have to convert it into objects again. You don't need to do that in Akka. You don't even have to make a connection in Akka. You just say, I need that other actor, and in config, it will say it's on a different machine. We use it in code, but you could do it in config, by the way. It feels much more natural, and another advantage is because it's like programming on a single system, you could even run it on a single system and unit test it. So for a bit of quality, I would recommend that you try this if you have such a thing. There's also one downside. In our case, we could use remote actors because we have a closed system. We don't have to version our messages. We don't have to think about independent technology, things like Java talking to .NET services or Java talking to some C program or stuff like that. It doesn't need to do that, so versioning is not a problem. But if you're running microservices, for example, I suggest you stick to REST and to JSON because that's versionable to some extent, and Akka messages aren't, because you have to share a binary dependency between them, and it has to be upgraded every time on both ends. Also, HTTP has more loosely coupled because of the versioning aspect. So, what does the use of remote actors bring us? Well, we have a highly concurrent system, so we don't need to worry about shared resources getting messed up or things breaking in that sense. Another thing is we have a built-in load balancer, which means that we could say, for example, if we have too much trains on a single train control, we could duplicate it and instantiate a second instance of that train control and go from there. So that it makes it more scalable. It's not like you have 100 trains on there, but you could do that. And also one other thing, we experienced that the wireless is sometimes breaking over here on the conference and on other conferences. And Akka has this built-in circuit breaker. What would happen if I can't deliver a speed message to my train, for example? In a RESTful world, you'd have to program a circuit breaker by hand. You have to catch that exception and ask, okay, why does this exception break? I don't know, is my connection gone? Is my serialization wrong? What's happening? And I have to decide for myself what's going to happen. It's not really easy to do that. In Akka, you have a built-in circuit breaker, so if it fails to deliver, it will raise an exception. And you can use supervision to say, okay, this didn't deliver. No problem, I will try again. And this way you prevent the train from going wild or stuff happening that shouldn't happen. So it's a very useful trick to have in your toolbox if you're running Akka. So that's a little bit about the software that we use and the reason why we build it this way. And on a hardware level, we have a couple of things involved. We have switches. We don't have them right now, but normally you can control the switches through Akka by sending a message to them. Use a couple of servo motors and a servo control board, which will translate the signals in the correct way. Obviously, we have the infrared because we have Lego normally uses infrared control to communicate with the train motor, but yeah, we replaced that. So normally they use this kind of remote control in the train, and the idea behind it is that kids usually we would have voltage on the rails. In an old train, if you have a train like 15 years old, you have voltage on the rails. And kids these days don't like that anymore. I don't know, it isn't allowed anymore, so Lego switched to infrared. And there's this Japanese guy, of course the Japanese, he went ahead and he reverse engineered the whole thing and wrote it down on his blog how it works. And we practically took that code and converted it from C to Java and later on into Scala messages and used that to control the train. Our train has a cool thing. It also plays sound. We can show that later. We added a battery-charged speaker to it, and you can use that to play sound on the train. Because what's a train without train sounds? I mean, it's pretty boring otherwise. And if you're feeling especially lucky today, we have a couple of RFID chips among the rails, and what you can do with that is we've built an autopilot program for the train, and it is location aware. So if it crosses a certain point on the rails, we could say, okay, Ferris wheel, go clockwise at a speed of 5, and if it crosses another point, go anti-clockwise at a speed of 2. Things like that you could do, and that's pretty cool to do as well. And since you can control the train from a remote location, like your work, if you're feeling bored out by all the other stuff you're doing during the day, you could control your train through your telephone. And then it's handy to have a camera on there. We have added a camera to the blue train, and you can see where it's going. And if that's not enough, there's also an overview camera which you can use to overview the whole track. So how does this work? There's an open source project that has a Raspberry Pi camera control. And we use this code to build a front end for it so you can see what's happening. It works like this. The camera is taking screenshots constantly. It's taking frame by frame and it's sending it over the network. And we have a small JavaScript file in there that contains code that basically just refreshes the images every few milliseconds. It costs a lot of bandwidth, but video does too, so that's kind of cool. And our Rails is cool and everything is nice over here. I can play with that, my kids could play with that, but we want to make it even cooler, so we added a ferris wheel, which you can control in exactly the same way, using infrared and a Raspberry Pi. And it even has an indicator of how fast it's going. Through a particle photon that controls the LEDs, and it shows you in which direction the Ferris wheel is going and how fast it's going. And this is a particle photon. It's a few centimeters big. It only has GPIO pins, so you can't do a whole lot with it, but yeah, it's kind of cool. And it has this unique thing about this device is that it's connected to the cloud, so you write your code in a web browser, actually. It's not like you have to use SSH clients and all that stuff. It does that all automatically. So you write your C code that's Arduino compatible, by the way. You write it in your browser, and when you're done, you say publish. Publish this to my device, and it will automatically upload it through the internet to your device, and it will start to run. It's really cool. My colleague is going to explain a little bit about the rest of the software we are doing.
Yeah, thanks. I think you forgot to show the Wally, wasn't it?
Yeah, we can show the Wally.
So we will show the Wally. I mean, you do it?
Sure. It falls off the table. It's not my fault,
I will
right?
first show it. Is it visible? So this is like the same infrared receiver as we use on the Lego trains. The engines are not the same as on the trains, because in the train you of course have wheels, which are directly controlled by the engine. But these are practically the same ones as we use for the Ferris wheel, to make the Ferris wheel go around. And we have a battery pack, which is essentially the same battery pack as we have on the Lego trains. So it's more or less the same, but I mean, Wally is probably even cooler than a train, so I had to get one. And we will show you how it works.
Hopefully it works.
Oh, yeah, we
just have to turn it on, that's all. This Lego set for Wally, it's normally a static thing. You can't control it, but there's a description on the internet how to add a couple of motors and a battery pack to control this sort of thing. And you can see it's pretty cool. and sometimes I get out of reach. That's also the thing. That's the reason why we control it through a Raspberry Pi with infrared. The range from my remote control to the robot is really short, so.
Yeah, if we use the USB Wi-Fi dongle on the train, I mean, we have endless reach as long as you have some Wi-Fi. And that's a big advantage. I mean, when I started playing with these trains and went from my living room to my kitchen and tried to stop it, it didn't stop and just crashed in the kitchen. Yeah, you don't really want that. I mean, then you cannot make cool big layouts of your trains. But it's nice to play around a bit with like Wally, but for like serious training, yeah, I mean, you need a bit more advanced setup. And to show a bit of what we did for software and what applications we built to control it, I will show you the rest. This is a bit of a summary. I won't read them all. It's probably quite common stuff. So we more or less used first Java and later Scala and Akka as sort of an interface integration layer between all the different components. So on the lower level, we still have some C code and some Python code to control the LEDs, or not the LEDs, the infrared transmitter and the RFID and the servos from the track switches. So we still have some low-level code, and we call that through the Scala layer. And that works, but my colleague is already working on sort of abstracting that away so that we only need to use Akka code and don't have to rely on C and Python code anymore. So that would be even easier for us to start adding extra stuff and improving it even further. This is a bit how it looks like, but I mean, it's just static, so why not just do a demo? Because, I mean, it's Friday the 13th, what could go wrong? If we are lucky, a train starts moving. We can make the Ferris wheel go around. And if you look here, the LEDs show the train speed, so it's now moving at speed 3 backwards. It's automatically updating. If you send new speed commands to the Ferris wheel, then the photon will also get an update with the new speed and display it on the LEDs. At the front, the large LED strip, it shows the speed of both trains. So only one train is now moving at speed 3. The other one is waiting, so I will enable that one. And it's moving at speed 5. You can see it is catching up on the other one. You see the camera at the top. The camera here, it's the overview camera. The camera on the train, we had to disable it because it uses quite a lot of bandwidth, and with all the Wi-Fi here, that's really tricky. So to make our demo go a bit smoother, we decided to just disable that. And we also have some train sounds, because, I mean, you need some train sounds. So that I can use to scare my wife when she's at home and I'm at work, of course, during my lunch break, playing with the trains. You see some of the Lego minifigures at the top. That's more or less to control the track switches. But we didn't bring them because it's a bit hard to set them up with a lot of wires and stuff like that. So it takes a lot of time to set up and break down. And we have to break down quickly after this session. So we decided not to bring them. We can view the different cameras. We can do some stuff with the LEDs, like increase the brightness, and then they get quite bright and annoying. So I put it down a bit. We can also do like standard animation. All the LEDs are individually controllable, so you can more or less do anything with it. We can change it back so that it catches up with the speed. Speed is only shown again when we adjust the speed. So when I again... now you again see all the speeds moving. And what we have is like an autopilot. So we have like two kinds of autopilot. This one, for instance, we can send a set of commands to the Lego train, like speed commands. You see it at the right. Oh, it's not the train, the Ferris wheel, I'm sorry. So we send a couple of speed commands, a sound command. We can do a lot longer list. So this is one of the things we can do. And another thing we can do is, for instance, this one. Now when the blue train, which has the RFID reader, reaches the station, the white train will start moving at speed 3 forward. When the blue train is reaching the crossing, the white train will move backward with a speed of 3. So then we can control the different components. And we could even do that with the blue train, that is, if the blue train reaches something, that he should go the other direction or whatever. We also thought about adding things like collision detection and stuff like that, but that's for more or less the next phase, because that's quite hard to implement, and we didn't manage to do that yet, but we got an intern who's going to work on it for the next half a year, so that saves me a bit of time, hopefully. So that more or less is a quick overview of the application that we built to control it. For now, I make sure they stop, because else it's a lot of noise. Yeah, so this is an example of the autopilot with some extra commands. I mean, we can tell you, yeah, like we really liked remote actors, and we can tell you, they're cool, Of course, I mean, our opinion. But we tried to get some figures to back our coolness, more or less. So we started to compare some facts. For instance, with Scala, you can create like fat jars. And fat jars are really easy, because you can just put it on a machine where Java is running and then just run it with Java. You don't need any application server or whatever. You can just start it, and it packs all the libraries that you need. And what we see here is that if we make a package with only the local actor, it's like 8 megabytes. If we add a remote actor, it's like 11 megabytes or 12, cannot see it exactly. But if we remove the remote actor and we add Akka HTTP, which is used to enable REST, so you can do a bit of JSON REST in your application, you see the amount of libraries that you need is huge. To do JSON, to do XML, you need lots of libraries, and if you just use remote actors, you need a lot less libraries. So from a library perspective, it's already a lot more friendly. And I made a bit of a comparison with Spring Boot. You can see that that compares a bit to remote actors. Akka HTTP is still fairly new, so maybe they can optimize it a bit and exclude some dependencies and make that size go down a bit as well. But we really think that remote actors is a nice and clean solution without having to add lots of extra dependencies. Next to that, I mean, Gatling is really popular, so I won't give lots of information about it, but Gatling is a performance test tool. If you want to know more about it, you can find a lot on the internet, but I will just show you what we did with it. So this is an example of how you do performance testing with Gatling. It's written in Scala as quite a nice way of testing. Before I did tests with JMeter and tools like that. They're quite hard to learn, a bit of a steep learning curve. With this one, you can just read a couple of pages, and then you know more or less every feature that is available with Gatling. So it's really a convenient tool. And what you see here is I simply define a scenario, and I want it to be repeated 100 times. So everything that's after the 100 times gets repeated 100 times. And what we do is we do a ping request on localhost, and we check if the status is 200. So basically, if I get a good message back. And then I did like a couple of runs. So I did a set of runs where I did a pause after each request, a 100 millisecond pause. And I also did some runs where I didn't do a pause and just sent a lot of requests at it. And in the end, we see that I started the user. So 1,000 users get built up in 10 seconds. So it's a bit shared over the 10 seconds to not overflood it from the beginning. Of course, if you have like a real system, bigger system, then maybe you want to do more than 10 seconds, but to do a quick test, this is really helpful. And we did this with a couple of situations, and we did 3 test runs for every situation that we tested, and we took the average of that. And we will show the details of what came out of that in a second. But first, to show you what we actually tested. So the stuff on the left side, so from JVM1 to the left, it's the same for both scenarios we tested. So we had an Akka HTTP application running in one JVM. And on the right, we had in scenario 1, we have another Akka HTTP, so we do a REST call with JSON to another JVM on the same machine. And at the lower one, we do just a remote actor call to another JVM on the same machine. So this is basically to compare a HTTP call with a remote actor call. And now for the numbers. I mean, of course, you shouldn't trust numbers you didn't falsify yourself. But I did my best to make sure that the numbers weren't falsified too much. So what do we see here? I mean, we see that remote actors, the mean response time in milliseconds, it's way quicker. The remote actors are the ones in orange. So, I mean, that's a clear win for remote actors, isn't it? And the same more or less goes for the max response time. And to show you that I actually didn't mess too much with my results, you can see the large green bar. That's basically a measurement error. I got some high results and I thought, okay, maybe I can filter them out, but then it felt a bit like cheating. So I was like, okay, you can already see the line going up, and this is just a measurement error. So I didn't filter any results, just took the 3 runs and took averages of it and displayed them in this graph. So again, clear win for remote actors. A 99 percentile, which it's commonly used at big enterprises. They use the 99 percentile to measure performance, and it has to be of a certain level before they go to production. And again, a clear win. So, it's easy, isn't it? But we were like, okay, so now we've done a bit of Akka comparisons with HTTP and with remote actors, but probably lots of you don't use Scala and Akka yet. So we thought, okay, let's compare it with Spring Boot, because that's quite popular and maybe a bit closer to what lots of you are doing at the moment. Although I say I didn't try to cheat too much and to not optimize too much. I mean, you can optimize performance tests by changing values like timeouts and stuff like that. I tried not to do that, but when I used Spring, I almost immediately got a crash. We were using the REST template to do a REST call to the other JVM, but with like 200 users that already broke down. And yeah, I mean, with Akka I already had like 1,000 users that was working fine. So I did a bit of investigation and I was like, why isn't it working? So I changed a bit of parameters, did a bit of Googling, and then I found a blog of a guy who said like, yeah, but the default connection factory that the REST template of Spring is using is practically not production ready. You should use something else. And apparently there is an Apache HTTP client which offers a nice connection factory which is working really good. So I added that one and I got way better performance. So of course, I mean, these are just some numbers in my case, but if you do performance tuning, it will completely differ. But this gives a bit of an indication on a comparison. And what we see here, I mean, I wasn't really happy about it. I mean, remote actors lose a bit. So I was like, oh man, how do I change the results to still get a positive image? I mean, else I cannot really do the presentation. I mean, I have to say remote actors suck and just walk away. But then I went a bit further. I mean, these are the mean response times in milliseconds. So here, remote actors clearly lose. But if we look at the max response times, remote actors win again, which we can see to the right. I mean, at the left, they still lose a bit, but on higher load, they start winning. And a lot. I mean, the max response times of Spring are a lot higher. So if you don't want too many really high response times, then again, remote actors seem to be like a good solution. And we see that again if you look at the 99 percentile. So although this is just some figures, I think it gives a good indication that remote actors, they can catch up quite well with REST. Maybe in some cases they're a bit faster, some cases a bit less fast, but we think they're quite a good solution for these kinds of things. Challenges? Yeah, no, we didn't have any challenges. It was really easy, so. No, actually we had a few. A couple of weeks ago I tried to add the servos with the adapter, and you need a servo board to connect multiple servos to a Raspberry Pi, because a Raspberry Pi cannot do that directly. So I thought like, okay, what do we do to fix that? I added some wires, and I did it before. We have 2 of these setups, so that was the second one, and I connected everything, went to do something else, because it takes a little while. Raspberry is really quickly, so starting up an application will take a minute or 2 minutes. So I was doing something else, and then I thought I'd try out if it was working. Didn't work, so I was like, okay, let's see if the wires are properly connected. Maybe they got a bit loose. And then I felt like, oh, it's actually quite warm. So I touched it. It's really warm. And that was the end of my Raspberry. Apparently, I connected the adapter to the wrong port, so luckily they're cheap. Another thing we had was with the Raspberry Pi A+ models, so the smaller, less powerful models. We use them in the trains because they're a lot smaller and consume a lot less power. But they're also built a bit cheaper. They have a bit cheap USB connectors. So what happens is if you have a bit thick USB device, like a Wi-Fi dongle, which is apparently a bit thicker than using like a mouse or a keyboard, then the pins, instead of making sure that your USB connector is fixed, the pins bend back when you enter the USB device, and that practically is the end of your Raspberry again. So that cost me 2 other Raspberries. So, I mean, playing with hardware, it's a lot harder than playing with software. I mean, if something doesn't work, you fix it and you can play again. But if the hardware is broken, you need to order new stuff. And so if you start doing this, it's good to order some extras, some reserves, so you can just keep on playing. So it's not really plug and play. I mean, even the documentation on the internet sometimes it's not much. Especially depending on what you're doing. I mean, we found out for Raspberry Pi, there's a big community. If you have any issues, most of the time you can find the answer on the internet. We also played with Odroids, which are comparable boards to the Raspberry Pi, but I didn't really get them up and running. They had heat issues, at least I think that was the issue. But they would break down after half an hour, and I had 2 of them, and they all broke down. I think it was due to the fact that they didn't have any heat sinks, so I could have added those heat sinks, but in the end I decided to just buy new Raspberry Pis because they had quad cores also by that time. Before that, Odroid were the only ones with quad core mini boards, more or less, that were still quite cheap. And you still have lots of options. I mean, we're all Java programmers, so we know for everything we choose, we have like 30 options, 30 libraries to pick from. It's the same when you do things like that. I mean, when I started with the boards, I was like, okay, Docker is really cool. I want to have Docker on a train, running my stuff, and that would be cool. But then, yeah, Arch Linux offers excellent support for Docker. It's really easy to set it up on a Raspberry Pi. But Arch Linux doesn't really offer any support for things like the camera, or it's more or less the other way around. The camera is built specifically for Raspbian, and some other things that we use are specifically built for Raspbian. So in the end, I was like, okay, forget about Docker for now. I just use Raspbian. And of course, I mean, I read people doing Docker on that old Raspbian version, but then you had to do cross-compiling and everything. And I was like, okay, that's too much effort for now. We just run it without Docker, and maybe in the 2.0 version, we will add Docker with a new Raspbian version where it's easily supported. Another issue is, I mean, if you have kids at school, you can play around with the Lego together. I mean, have a good excuse to do a bit of Lego playing. But if they are too little, it's a bit of a challenge because they tend to break up stuff. And that doesn't help a lot. And I think the biggest challenge was time. I mean, at the beginning, we thought, how hard can it be? We add a few infrared transmitters and some other stuff, and couple of evenings and should be up and running, but in the end it cost a little bit more time than that. But we had some help from our Lego friends. So what about the future? This actually was a Lego set you can buy. I don't have any stock options, but I think it's quite a cool set. So what we wanted to do is use the Reactive Pi library. My colleague that just helped me with the presentation build. So with that, we can easily just use Scala and Akka and remote actors to send events to the Raspberry Pi ports, and we don't need any C, Python code anymore. So that's a lot easier. And as I mentioned already, we want to do something like collision detection so that we can make like autonomous driving Lego trains. I mean, Google does cars, but I mean, everybody can do cars. We will do Lego trains. That's the real world. Lessons learned. So, yeah, what did we learn during the project? I mean, you can run like enterprise software. The things we're running on big servers, you can easily run them on Raspberries, even on the small ones. And of course, if you do a lot next to it, I mean, we also have the camera attached and some other stuff, then you start to reach the limits of the memory. It has 256 megabytes of memory, and that's a bit tight. So we just, we can manage, but just barely. But if you use the quad cores, they have a gigabyte of RAM and lots of processing capacity. That's quite easy. You can practically run anything on it. Yeah, the rest first remote actors, I think you already saw from our presentation that we really like this. It's really nice, more natural programming approach than using JSON, XML, or something like that. And also the particle photons, so the small things we use to control the LEDs, we think they're really cool. But unfortunately, I didn't see somebody run Java on it, but still they're quite cool. And of course, yeah, playing with Lego, it's awesome. What do you want more? But to show you that there's even more, I will show you a little video. No, not that one, this one. So maybe some of you can already guess what's going to happen, else you have to wait for like 30 seconds to see what is going to happen. So here you can see I can control the trains with my mobile phone. I can just move speed forward, stop them. Yeah, there was one piece I failed to automate, unfortunately, but my wife luckily was really helpful assisting me. And sorry, I have to apologize. I already drank all my good Belgian beers, so there's a Dutch beer on the train. Sorry. But I mean, this is really helpful. I mean, you don't have to get up from your chair if you're watching a movie. What else do you want? So we reached the questions part now, and instead of just displaying this slide, I will display a movie, and during the movie you can just have just ask any questions that you have. So this is a movie from my home. It also shows you the switches and some other stuff that we built into it. So any questions? Just shout loud because I only see like lights and the first few rows. I see someone waving, yeah.
Why didn't you use Spray instead of Akka HTTP until it's speed optimized?
Okay, so the question is, why didn't you use Spray instead of Akka HTTP? Yeah, we looked at it, but we thought, Akka HTTP, how difficult can it be? We just used that. But of course, I mean, you could have used Spray as well. I don't know if speed differs much. I didn't do any performance tests between those two. Yeah, it differs a lot? Okay, so for everybody that is going to work with Akka and wants to have REST endpoints, apparently still Spray is the way to go. So I think that's a good addition.
The Akka HTTP is the second version of Spray.
Yeah, yeah.
It's the first version that is live, and the next version will be more speed optimized like Spray is.
Okay. So if I understand you correctly, it's best to use Spray or wait for the new Akka HTTP version.
Or if you're feeling really lucky, go to 2.0 milestone 1 and then break all your stuff, basically. Yeah, okay.
Okay. Any other questions? Please just shout or wave really.
I have a second one.
Yeah, of course.
Does it make sense to use type vectors instead of the normal ones?
I don't know. Yeah. Like, we chose one option and went with it. That's it. I mean, there's no other excuse to do this. Yeah.
Okay, other questions maybe? Yeah, I see one at the front.
What is the future of your project? I mean, how do you see all these things be implemented in the real world? And do you have any propositions, any interest shown by big guys?
Yeah, so the question is, how do we continue with this? Can we make any business value more or less out of it? Can we sell it? Well, we already had some people asking like, hey, do you sell this? And I mean, I read a Picasso was sold for like 180 million, so we can probably sell you a train and a Ferris wheel for it. But no, it's not our business, more or less. We build software. So this was partly just to investigate, do a bit of research, play around a bit, get more knowledgeable about Akka and stuff like that. So we don't have direct intention of selling this, but we actually got from quite a large company in the Netherlands a request of can we show this to their developers and maybe let them participate in it a bit so they get more knowledgeable about IoT and working with hardware. So in that respect, we might end up making money off it, do some consultancy, I don't know. But it wasn't our intention. I mean, we just wanted to play around a bit, have something visual, which we could show to others. So that's more or less it.
And of course, if you think about building IoT solutions and writing C, I don't know if there are many guys doing C right now. Can you raise a hand if you do any C development?
I see a few.
A few. So there are just a few of us that do this. And if you think about it, it's a lot easier to write Java. But the problem right now is there is one tool that does this kind of stuff. There's Py4j, that's a free library, but it has a GPL license. And if you're doing any commercial development, that's a bad thing to have. Because there's no way companies are going to share their code that they use for their client together with the library like Py4j. So instead we went ahead and built a library that does the same thing, only through Akka and Scala, but it has an Apache 2 license. And that's basically also the idea behind this. Get these libraries out so people start doing it and see from there what happens.
I saw another hand, yeah?
Do you plan to use the camera for collision detection?
Yeah, so the question is, do you plan to use the camera for collision detection? I did a bit of investigation, and apparently you can do things with cameras, which also have like ultrasonic sensors. So there are a few solutions, so we still have to investigate, and I hope my intern will do that for us. I did a bit of research, and it's a really broad field with lots of scientific papers about it. It's quite interesting, but I think it requires quite some time to implement it carefully, because if you think about it, it's quite easy. I mean, you just detect what's in front of you, and you're okay. But what if you have a track switch and two trains go like this? I mean, in front of the trains, nothing is happening until they crash together. So you need like sensors at the sides or something like that. So then it starts getting complicated quite quickly. So I don't know yet what we will do. It's, I think, a matter of experimentation and more, getting more knowledge about it. But if you have a good solution, of course you can help around. Other questions? Yeah?
How much time did you spend?
Okay, so the question is, how much time did you spend? I don't know, and if I knew, I probably wouldn't say, but then my wife would be really angry with me. No. It started in lots of evenings, weekends, and later on when it was like, yeah, we got it more or less up and running. We used it at talks like this. Then my manager decided, okay, we will give you some time for it so that you can also do it during the day. So I'm so lucky that my employer paid me to play with Lego, so that was really cool. But I have really no idea. It's a lot. I think a couple of work weeks easily. Because we didn't only make this one, we have like 2 or 3 of these sets, so it's quite a lot of work to get it going. And in fact, I mean, you could see like the track switches there. They have what's a paperclip?
Yeah, we bent on the paper clip out, and that's the most expensive part of our train. Actually, it took 3 people, 100 euros an hour to complete that. So 300 euros for a single paperclip. I mean, yeah, you could get a whole pallet full, I think, for that amount of money. So things like that, you think, oh, it's just bending a paperclip, but if it's just too short or a bit too long, then the switch doesn't move properly anymore. So everything is a bit tight fit, lots of customization, trying around. So it costs you quite a lot of time. But actually, I mean, first setting up the first set took quite a lot of time. Setting up the second set, it went really quickly because we already had the programs and everything. We knew which cables to connect to which ports and everything. So second time it goes quicker. So if you have to do batch production of it, we could probably increase the speed even more. So if you're interested in buying 100 sets of it. And the other hardest part is actually trying to find out how drivers work in Linux. Linux has this kernel space and user space and lots of magic numbers and stuff like that. It's quite hard to get right. And I don't know if any of you guys have ever read the kernel specifications from Linus Torvalds and other guys. Those are quite hard to read. That's a lot of text to get through before you can even think about controlling a switch. So, yeah.
Any other questions? I don't see any hands, so then thank you for your attention. If you have any questions remaining, feel free to contact us afterwards through Twitter or come here, just let us know. And thank you again for showing up.